All right, so welcome everyone to our final colloquium of the 2020-2021 academic year. Really fortunate to have with us today Dr. Javier Duarte from UC San Diego. Dr. Duarte, actually, this is kind of interesting. So Dr. Duarte did his undergrad at MIT. In fact, you and I overlapped. I was a grad student while you were an undergrad. And I'm sad that I never met you back then. Here's the interesting bit that connects to this semester's colloquia. One of our earlier speakers also did her undergraduate research with Janet Conrad at MIT. Her name is Tess Smith, and she's at LBL. And it is also a sort of focused on, well, in her case, neural networks for molecular systems. So pretty cool. I don't know if it was that working with Dr. Conrad gave you all something there. Was it a seed?
Yeah, it's very interesting. Yeah, I also chatted with her because it's interesting. Our work kind of was similar and then diverged, and then now like is similar again. So
yeah. All right. So Dr. Duarte got his bachelor's in physics and math also, right? From MIT in 2010. He received a PhD in physics from Caltech, working with Maria Spyropoulou. And then for 3 years was a Lederman Fellow at Fermilab, and that's a fellowship named after the Nobel Prize winning particle physicist there. And since 2019, he's been an assistant professor at UC San Diego. And as you no doubt all saw from the abstract of his work, he's interested in high energy particle physics and the application of artificial intelligence techniques to understanding the data that emerges from these experiments. So Dr. Duarte, thank you again very much for joining us today, and I'm looking forward to your talk.
Thank you, Paul. Thank you so much for that lovely introduction. So yeah, as you said, today I'll be talking about particle physics and AI, and I titled my talk "The Edge of Particle Physics." And there's essentially two meanings in this. One is in computing, we call edge computing anything that's right on the sensor, right close to where the data is being collected, and that's one meaning. And the other, of course, is we're at the edge of our knowledge, so that's where we're trying to explore. And one thing I wanted to, and also feel free to ask questions and interrupt. I'm very used to Zoom at this point, hopefully. So if you have questions, feel free to raise your hand or interrupt, and I'm happy to make this more conversational. Okay, so one thing I wanted to start with is just to say, particle physics, unlike maybe some other disciplines, well, I mean, things are getting bigger in other disciplines as well. It's very much a team effort. And in fact, it's more than just a team effort. It's a global effort. But these are just some of the pictures of my team at UCSD. So including postdocs, grad students, and actually many, many undergrads who are able to do research in this field. So that's one thing that I want to just emphasize, that a lot of the work that I'll be talking about, has had substantial contributions from not just graduate students and postdocs, but also undergrads. So it's very much a interesting place to spend time on, because you can actually get involved in research very, very quickly. Yeah, so as I said, so UCSD is actually one part of this global effort. So just showing here are a bunch of the locations of other institutes in the experiment I work on, which is the CMS experiment. And you can see that we're spread out all throughout the world, and UCSD is just one of the many collaborating institutes on this more than 3,000 person experiment. So of course, we work with a lot of international collaborators, at various locations. These are just some pictures of kind of close collaborators, again, whose work will be represented in this colloquium. And then, of course, when I talk about CMS results, that represents the work of, physicists, engineers, and, like I said, over 3,000 physicists and engineers over many, many decades at this point. So it's definitely very much a team and a global effort that's going to be represented here. Okay, then one other thing I wanted to kind of sort of make you think about beforehand, and I'll answer the question at the end of the colloquium, but maybe people will have their own answer. I guess people could also look forward in the slides. But the question is, so what do Mars exploration and particle physics have in common? Of course, it's an open-ended question. You might think of something that I haven't thought of, but that's just something to keep in mind as you listen to the talk. Okay, so in terms of particle physics, then we have to think about, so what are we studying when we study particle physics? Right now, our best description of the subatomic particles comes from this theory called the Standard Model. And the Standard Model is basically composed of two ingredients. It's a model that describes fermions, which are on the outside of this ring here, which constitute matter. And these interact via forces carried by bosons, which are these all other particles that, again, can mediate these interactions between these particles. And so the Standard Model has these two pieces. One is basically the list that you're looking at here, the list of particles and their properties and how they and what they are. And the second piece is how these particles talk to each other. And so this is represented on this graph here, which is, I feel like I can stare at this for days because the connections are so intriguingly symmetric, but yet slightly asymmetric in a way that makes you think about, big theories and how something must have been broken and how there must be a bigger picture that this is just showing us one slice of. And so you could really just stare at this and see all these subtle connections. But what this is showing is it's showing a line connecting each of the different particles. And that line tells you whether these two particles interact with one another. And so far, and we also know there's other parameters of the Standard Model, things like the interaction strength, so how strongly these two particles can interact, and a few other parameters. So it's about 20 parameters of the Standard Model in total. So that's it. That very simple, basically the two pictures I'm showing you and then a bunch of numbers, that's basically it. That's all you need to describe the particle physics currently. But we know there has to be more to it than that. Because like I said, one of the things that's so tantalizing with this graph is there's so many why questions you can think of. Like, why is it like this? Why is this number and not some other number? And so far, the Standard Model is really just a description. It doesn't explain why something is the way it is. It just says, okay, here's a description, and this description turns out fits the experimental data very well. Moreover, there's unexplained phenomena. There's things that we observe in the universe that the Standard Model does not include, that the Standard Model does not even describe. So things like dark matter, the fact that we know dark matter exists in the universe and is not described by the Standard Model. The fact that one of these particles, or three of these particles actually, neutrinos, they actually have masses. That's not really explained or described well in the Standard Model. And there's also the fact that there's a huge matter-antimatter asymmetry in the universe, which is the fact that there's way more matter. We don't observe antimatter galaxies out there. We just see matter galaxies as far as we can tell. And so this big matter-antimatter asymmetry doesn't seem to arise naturally from the equations of the Standard Model or from the symmetries of the Standard Model. And so there seems to have to be more to it than this. And one way we can explore, what things could be there is using the Higgs boson. So as you can kind of tell from these two photos, the Higgs boson is really a centerpiece of this model. All the particles seem to interact with it. And actually, it's responsible for giving rise to the mass of these other particles, which I'll explain on the next slide of how that works. So in particular, since if there are any new particles out there and they also get their mass from the Higgs mechanism, then it may be a link, or it may tell us about how, basically it may give us a hint as to what new particles are out there, because we know it has to interact with it. So if we study it very precisely, it can tell us about these new particles. Okay, so a quick digression on what the Higgs mechanism is like. And so I'll show you this quick video. One thing to remember is that actually all these particles you can think of as there's actually fields. There's fields that are extended all throughout space, and particles are basically excitations in this field, so little waves in this field. And so the Higgs field is just like this. You can imagine like something that's spread out all throughout space. And in this case, the Higgs field is represented by people at a cocktail party. So if you have a bunch of people at a cocktail party, and again, these represent the Higgs field, and you have somebody who comes in who's, let's say, somebody who's not very popular, let's say like a tax collector that nobody really wants to talk to. Well, that tax collector will be able to walk through that cocktail party very easily and not interact much with anybody. And because nobody will really stop and want to talk to the tax collector. And so what this represents is this represents a very low mass particle. So basically a massless particle that can interact, that basically doesn't interact with the Higgs field and can just zip along the room and from one side to the other. On the other hand, if you have somebody famous, like let's say, famous physicist Peter Higgs, for whom the Higgs boson is named, enters this cocktail party, and let's say that it's a cocktail party full of particle physicists, so they all know who he is, then instead of him being able to zip on by through the cocktail party, he'll in fact get sort of stopped because people will want to like ask him questions. Okay, maybe this is pre-COVID, so people aren't wearing masks and getting closer than 6 feet, but people are going to want to, essentially cluster around Peter Higgs, ask him questions, talk to him, and it'll take him a lot longer to get across the room. So what's happening here, the analogy is that this Peter Higgs is like a massive particle that interacts with the Higgs field, gets stopped, and basically has more trouble getting through this field. So it's like it has like inertia. And that represents like what mass is. Mass is really not a property of the particle, but it's a property of the interaction with the Higgs field. And lastly, one thing I wanted to point out is, okay, so what's the Higgs boson itself? So the Higgs boson itself, the analogy you can think of is, what if somebody shouted a rumor or shouted something intriguing from one side of the room to the other, but you couldn't quite hear it on the other side. So instead, people might cluster to like hear the rumor or hear the interesting story and then tell each other it in like a game of telephone. And this will create this kind of clustering that moves across the room. And so that clustering or that wave, that excitation that moves across the room, that's basically the Higgs boson. A Higgs boson is like a localized excitation of the Higgs field that you can measure, that moves across moves across space. Okay, so that's just a little bit of an explanation of, or analogy for how the Higgs field works and how it gives rise to mass and how it's so fundamentally important. So how do we study it? And all these other fundamental particles as well. Well, the way that we study it is to actually smash particles together at the highest collision energies possible and observe the remnants of the collisions using enormous detectors. So the world's biggest collider currently is the Large Hadron Collider. It's located at CERN in Geneva, Switzerland. It's 27 kilometers in circumference. And so it's shown here. You can see the mountains in the background. And just to give you a sense of scale, if I take those 27-kilometer ring and just plop it on Northeast LA, you'll see, so if you have one side of the collider is, cutting across campus of Cal State LA, then the other side of the ring would actually be basically all the way in Silver Lake. And you would actually also one side of the ring would be, reaching Highland Park, and Dodger Stadium would be entirely enclosed. You'd have another side of it too in downtown. So this would be like you'd have each of these points, for example, would be a new experiment that would be sitting on the ring. So just just to give you an idea of how big this experiment or this collider really is, I mean, it takes up a large swath of Northeast LA. Okay, so what is the Large Hadron Collider? So it's a proton-proton collider, which collides these protons at nearly the speed of light. The specific energy center mass energy is 13 tera electron volts, which is just a unit of energy that tells you that they're moving very, very fast. There's 4 interaction points situated along the ring. So at each of these interaction points, there's another experiment on a detector that's running and trying to observe collisions there. At each of these points, we basically bring the beam together and collide the beams 40 million times per second. So every 25 nanoseconds, there's another collision. And one collision actually doesn't look as clean as you might think. It's not just one proton hitting one other proton, but actually what it is it looks something like this. You have a train of protons hitting another train of protons, and they actually all hit each other and create, this spray of other particles. And so you see this like kind of mess, basically. We also call it pileup. which makes it actually kind of difficult because we have to disentangle one interesting collision out of these many simultaneous collisions happening. And just to give you a sense of how often something interesting happens, the Higgs boson might be produced, for instance, 1 out of every 10 billion collisions, which sounds like not very often, but actually because we have such a high data rate, because we need it, we actually get a Higgs boson about every 4 minutes. So that's one thing that we have to be careful about, is how we choose which data to analyze, because in the end, we can actually only analyze about 1,000 collisions per second. And this is just due to the fact that there's so much data coming out of each of these collisions that we don't have enough computing power or processing power to store it all. And so we need to just analyze a small fraction of it. And so we have to be very careful about which fraction we choose to make sure we're not throwing away all the Higgs bosons that are there, that we're keeping as many of them as we can. And so the experiment I work on, as I said before, is called CMS. This is a head-on view, so as if you're one of the protons coming in, and it's the one that's located in the left arrow over there. Okay, so actually maybe I can stop here for a second and see if anyone has any questions.
May I?
Yes, please.
Okay, well, aren't you worried that you are not analyzing all collisions?
Yes, I am worried about that. I work on this system called the trigger that tries to select the collisions that we analyze. And so I am a little, I am concerned about it. That is the thing that I am concerned about. But at the same time, one of the things that you're seeing here is that Higgs boson, so interesting events happen very rarely. Most often, what you get when you do these proton collisions is you get basically very slight small angle scattering of these two protons, such that essentially there's not enough energy transferred between the two protons for anything interesting or heavy or interesting particles to be produced. So instead, what happens is you just get this what we call background events, and I'll talk a lot more about these. But these background events. But these background events have been studied in great detail at previous colliders. So we don't actually need to keep all the background events to analyze them further, because we don't, basically we're not interested in the physics of those events. We're interested more in the physics of very rare events. And so we have enough bandwidth to save those rare events, but we just have to make sure our algorithms are accurate enough to save them.
So I guess my question is, do you save all the events, or do you only save 1,000 collisions per second?
So
in other words, is the number of analyzed the same as number saved? Is it the same as number that happened?
Yes.
Are there 3 different numbers?
No, there are only basically 2 different numbers. There's the number that are saved and analyzed, and the number that are produced. Yeah. So yeah, we analyze all the collisions we save.
Thank you.
Okay. Any other questions? Okay, and so let me zoom in a little bit on the CMS detector itself. So as you can see, it's actually a massive thing. You can see a person there for scale. It's composed, you can think of it as like a large camera that's essentially composed of different specialized components to measure different kinds of particles. So each of these detector components is basically looking for the signature of one of these different kinds of particles. And in the end, there's about 100 million channels. So you can think of it as like a 100 megapixel camera, where each of these channels is telling you some information that we then combine using our algorithms in order to reconstruct what exactly happened in each collision. So to give you an example of how this combination happens, so we can look at, for example, how CMS sees quarks and gluons. So quarks and gluons are fundamental particles that interact via the strong force. And one of the implications of that is they're never seen in isolation. They actually quickly undergo this process called hadronization and become jets of hadrons, which are bound states of quarks and gluons. So instead of basically making a very nice, smooth track in your detector, instead you see this spray of many particles. So this could be, for example, the signature of a single quark that comes in, it's very high energy, and then immediately hadronizer creates a spray of other quarks and gluons, and then these deposit their energy. So you see that the charged particles curve in the magnetic field, the neutral particles stay straight, and then all of the particles basically interact with the hadron calorimeter, one of the components, and deposit their energy and get stopped. And so what we do is we measure the tracks that you observe, that you see there, as well as the total amount of energy that's deposited. And we cluster all of this together into an object that we call a jet. And so that's this like cone-shaped object that you see here. And we look at the like total energy of that object and try to analyze it at that level. Okay, so then how do we make Higgs bosons at the LHC? So the LHC, as I said, collides these protons, which are made out of quarks and gluons. But actually, basically, most of the time, when you collide these two protons at high energy, you're actually colliding gluons. So the question then is, can we collide these gluons to make a Higgs boson? And so if you remember from that figure, there was no direct link between Higgs bosons and gluons. Gluons didn't seem to interact directly with the Higgs boson, which actually makes sense because gluons are massless, and the Higgs boson, the interaction strength with the Higgs boson is related to mass. So it makes sense that there's no direct interaction between them. But it turns out that you can have quote unquote virtual interactions, interactions that are generated through so-called virtual particles like the top quark. And the analogy here is you can imagine instead of just going directly from the gluon to the Higgs boson, you go through the path of another particle and then go to the gluon. And so what this gives you is, this gives you a link between these two particles, but not a direct link. And so what we do is we start with these two gluons. We can produce a Higgs boson through this top quark loop, we call it. And so a natural question is, if there's any new particles out there, like a heavier version of the top quark or new particles entirely, they could also contribute to this. They can also you can also produce Higgs bosons through the same mechanism, but with this new particle instead. And in fact, if this new particle is so heavy that it's hard to produce it directly, instead what it would look like to us is that it would look like the Higgs boson just has a new interaction directly between the gluons and the Higgs boson. So this is what we can look for, is we can look for this kind of direct interaction that shouldn't be there in the standard model, but could be a sign of new particles that we have not yet observed. Okay, so then that's how we produce the Higgs. That's how we produce the Higgs boson. But then, how do we detect the Higgs bosons? So one of the major ways that they're produced is through the decay. Basically, the Higgs bosons live so not very long, and so the only way you can detect them is through their decay products, what they turn into. And so most often they turn into two bottom quarks, actually. So this production rate is very large. So you might think that this is the easiest way to detect them, but it turns out it's very difficult because there's very large backgrounds in that there's lots of ways to basically make two bottom quarks. And so there's ways to make them without any Higgs boson involved whatsoever. And these other ways are much, much more prevalent. It's much easier to make these bottom quarks through just other quarks and gluons. And so the only thing we see are these two bottom quarks. And so we have to ask, basically, based on these two bottom quarks or based on the decay products, was it a Higgs boson or not? And so to put it more visually, we have an event that looks like what you see here, where the jet is on the left, and that's the one we want to analyze. We see it's a spray of particles with their tracks and their energies. So the energies are represented by these blocks. And then we measure, basically, so this is what we measure. And then we want to know is, did a Higgs boson create this, like in the top left? Or did a gluon create this? And the issue is that the gluons can create this up to 10 to the 7 times more. So this is just a much more frequent way for it to be produced. So that's one of the main goals. So can we use, for example, new techniques like artificial intelligence to help us disentangle these two things? Okay, so that's a very long-winded intro, but I'll stop here to see if anyone has any more questions. before proceeding?
May I?
Yeah, please.
Okay. Those two competing processes that you just mentioned, they look exactly the same to me. So are you going to explain how do you distinguish those two? I mean, the output looks the same.
The
You
output,
have gluon and bottom anti-bottom pair, right?
that's right.
So
they,
how do you know which one is which? I mean, which process led to this outcome?
That's right. That's right. So they are the same in terms of the particle, but actually there's correlations between the particles that are different. So in particular, one of the big differences, but it leads to other differences too, is that the Higgs boson is massive. It has a mass of 125 GeV, whereas the gluon is massless. And that essentially translates into an angle between the bottom quarks on average, like a specific angle between the bottom quarks. And we can use those kind of correlations, basically the geometric correlations between the bottom quarks and also the spray of other particles that is produced to tell them apart.
Okay, get it. Thank you. And back to the when you were talking about the processes that lead to the production of Higgs or even the decay. Like for example, why is the decay into bottom anti-bottom favored over decay into top anti-top when is there some simple physical argument to understand this, or does one have to go through some kind of long calculations to understand that?
No. It's quite simple. Yeah. So the Higgs boson's mass is 125 GeV. So to decay to two top quarks, so each top quark is about 175. So to decay to two top quarks, it would have to be at least as massive as 2 times the mass of the top quark. So it has to be.
Then it prefers the next most massive, right? Which is bottom.
Exactly. So it prefers the next most massive in terms of the fermions. And the reason why there's a kind of a general offset between fermions and the bosons, they have different strengths with which they interact. But yeah, in general, if you're just looking at the fermions, the hierarchy is exactly like their masses.
Okay. Thank you.
Yeah, no problem. Okay, so for the remainder of the talk, so for the first part, I'll talk about how we use AI to basically do this disentangling of the signal from the background, and then measure the Higgs boson, especially at high energies, because that's where there might be the most influence from new physics. And then I'll talk about how we're using AI at the edge of our data collection. Okay, so at low momentum, and I think this goes to your point as well, at very low momentum, the bottom quarks are essentially resolved into these separate jets. And it's actually pretty hard to disentangle, even if you know this information about the Higgs boson has a different mass, because there's just lots of bottom quarks, and it's easy to misidentify one quark as a bottom quark. And so it just becomes a very difficult challenge to do this at low momentum. But however, at high momentum, what happens is basically because of the boost or the energy that the Higgs boson has, when it decays, it essentially decays into this collimated, these two bottom quarks are collimated, or what we call Lorentz boosted, into a single large radius jet. So we have basically a single jet where all the decay products are essentially overlapping. And this actually makes it, sort of seemingly counterintuitively easier to identify, because in this single large radius jet, it looks very different from a lot of the other background processes of QCD. And in fact, then the only one that you really have to tangle with is this gluon splitting to two bottom quarks, where you also have it happening at high energy. And then we can still use AI techniques to try to disentangle these two. So to summarize, so then what our goal will be is basically to try to identify these high momentum or high transverse momentum Higgs candidate jets with both the jet substructure, so actually seeing what the jet is composed of and how it's organized essentially geometrically inside of the jet. We'll use this dedicated B tagging algorithm called the double B tagger, which I'll explain, is this AI algorithm. And then finally, we'll also use the jet mass. So the fact that the mass of the Higgs is different from the mass of a gluon, which is basically 0. And so what this means is that what we expect to see is we expect to see a smoothly falling background from other standard model processes, especially from gluons, and then a bump at 125 GeV, so an excess or a resonance, a higher number of events at 125 GeV corresponding to the Higgs boson. And that's what we'll look for. And so again, the main background is going to be this sort of QCD, we call it QCD-like processes, just means it's produced through quarks and gluons. In this case, the gluon decays to 2 bottom quarks. Or the other backgrounds that we have are W and Z plus jets. So this is a other particle that can decay to quarks. And in fact, the Z boson can also decay to 2 bottom quarks, and that'll be very useful. I'll talk about that in a bit. And another background is the production of 2 top quarks. Because again, this can kind of look similar in that you make 2 bottom quarks, although they're spatially separated. And then you can also have other quarks in the event. Okay, so then going back to how we can distinguish jets containing 2 bottom quarks from other kinds of jets, one of the main things is that these bottom quarks turn into B hadrons, and B hadrons have long lifetimes. So they actually travel a little bit, order of millimeters, before they decay. And we can actually measure that displacement using our tracking detector. So what we look for is basically some small displacement from the primary vertex where all the main collision happened, where there's this decay, which means that there's these displaced tracks from these other particles that come out of this decay. And these displaced tracks also have large impact parameters, which means that they're not very consistent with the primary vertex. So they do seem to have a very large displacement or very large momentum also. And also there can also be special, soft particles or low energy particles that are produced in addition that can help us to distinguish bottom quarks from other kinds of quarks. And then finally, this is talking about this jet substructure. We can look at the relative position of these so-called secondary vertices, which are where these B hadrons decayed, and see, because if the relative positions should be related to properties of the Higgs boson, the fact that it's either has mass or is is also a different spin than the gluon. Okay, so then we basically want to use deep learning because deep learning is this use of structured neural networks with many hidden layers to approximate the solution for any given task. So it's basically, it seems like a good tool to try to use. And we use them basically because they seem to work really well. Empirically, we find that they do as well or better than a lot of the algorithms we've used before. One of the reasons might be that we have lots of data and simulation in order to train them. And that's something that seems to actually also help with the performance of these neural networks quite a bit. Nowadays, there's these fast ways to train them like TensorFlow and PyTorch and software packages, as well as GPUs that can help you do this machine learning and has really democratized this. And then finally, one interesting idea is that by looking at our events in a different way using this tool, we may even possibly gain new insights about what's going on in our collisions. And so just to briefly explain what a neural network is, so this is showing a classic fully connected architecture. It's basically you can see this function where the inputs come in. In this case, the inputs are these green numbers here, and they're multiplied by some weight. These weights are going to be the parameters that we're going to vary of our function. These weighted values are then summed across all the inputs, and then you can add a bias. So this is, again, another additional parameter. You can see up until now, this is just a linear function. So it's just like yx plus b, or sorry, y equals mx plus b. So it doesn't seem to be anything super special. So really the magic happens in this extra function, which is called an activation function. So this is a nonlinear function, and you usually choose something that kind of mimics the biological property of at low energy, at low input, it's 0, but then at high input, it's 1, or it's above some threshold, you activate it, and that's where the name comes from. And so one popular choice for deep learning is something like a sigmoid. So it's shown here as like this function that smoothly turns on from 0 to 1. And so then you can apply the same logic to each of these cells. So each of these circles is a different neuron that you can apply the same logic to. And what we do is we actually train this algorithm, so with all of these free parameters, by varying them in order to minimize something called a loss function. And this loss function is basically something that quantifies how many mistakes the network is making, so for its given task. And one interesting thing to note is that a sufficiently wide neural network can basically approximate any function. So we know that if an optimal solution exists, it should be able to be modeled at least approximately with this kind of neural network. Okay, maybe I'll stop here, see if anyone has questions.
Muon is striking again.
Yes. How do you know what is a mistake?
Good question. Yes. So we need labels. So I'll talk mainly about supervised learning today. And that's assuming that you have labeled data. And so, for instance, classic example is like images. We can label the images as, elephants or dogs or so on. So we know what the labels are. In particle physics, the only way we can really label our data is by using simulation. So that's where that aspect comes in. Okay.
Yeah, thank you.
Yeah, great. No, but a very important question. Okay, so then to give another, so to give an example of what a deep neural network can do, so RESNET-50 is kind of a popular example, which is a deep convolutional neural network. And so it's pretty similar to the one I just showed, only it actually acts on pixels that are locally grouped, and the same set of weights is applied to each patch. So it's a subtle difference, but it actually helps because it knows something about the images. Basically, it knows that if if there's an elephant in the image somewhere, you should still classify it as an elephant, even if it's in the top left or in the bottom right. So that's why we're doing this convolution where the filter moves across the image. So other facts about it, it's 50 hidden layers, it's 8 billion operations. It might take a while to run on a CPU, but it has pretty good performance for natural images. So you can see this picture of an African elephant taken from Wikipedia. The predictions from it are 90% probability for African elephant. So it seems to do pretty good at that classification task. Okay, so then what about if we just apply it in the wild? So here I gave it a picture of my dog, Scully, who's probably running around right now. And she is predicted to be, at least based on this, has a Rhodesian Ridgeback with probability 50% and red bone with probability 28% and a bloodhound with probability 6%. So we recently did a DNA test so we can actually double check this. And the DNA test actually comes back with, she's a mixed breed, so she's probably a hard case in the beginning. But she is a high percentage of red bone coonhound, so 19.7%. And the rest, there is a large fraction of supermut as well. And the supermut might include Rhodesian Ridgeback, actually. So there is definitely some, so as you can see in the wild, it doesn't always perform perfectly, but actually did an okay job given that she might be a kind of a hard case. Okay, so what we can do is actually apply the same kind of principles to identify these jets. And so I just want to give you this as like an analogy. So RESNET-50 actually can almost be directly applied to doing jet classification. So for instance, if we wanted to classify top quark jets versus QCD jets or jets from light quarks, you can see that on average, these jets are very different. For the top jets, there's three quarks that are inside of the jet. And so there's a lot more of a spray of energy versus for these light quark jets, there's basically the energy is very much localized in the middle. And these are average pictures of many, many jets. So you can get an idea of like there is a definite difference between them on average. But for any one individual jet, if we looked at just like a 2D picture of it, you would instead see that actually it's kind of hard to tell them apart. You can still kind of see on the left that there is like these three, clusters of energy for the top jet. And on the right, you can see that there's really only one cluster. But in general, you could see why it would be difficult to classify these in general. But nonetheless, actually, we find that ResNet-50 can actually perform this job and get up to like 99% accuracy based on this, these different kinds of images. So that's just to give an example of how we can use this in physics examples. In practice, though, we don't always just reuse existing architectures. We actually design our own. And so for this particular case where we're interested in two kinds of inputs, so tracks as well as secondary vertices, and actually in this case, we have a third input, which are kind of like expert features, which we handpicked, which we know do a good job of discriminating between Higgs jets and other kinds of jets. We can use a custom architecture like the one shown here to actually do this discrimination. And so the names here are kind of maybe a bit unknown. You may not be so familiar with them, but you can just rest assured that they're just different kinds of neural networks which apply in different ways. So for instance, in the first block, we just have the same neural network is applied to each track or each secondary vertex. And in the second one, there's this recurrent structure in the network, but basically what it's doing is it's summarizing a lot of features and it's trying to cast them down to a lower number of features. And then finally, this final classification layer basically just takes this input and runs it through a regular fully connected neural network. So this is just an example of the kind of architecture that we use. And so what does the performance look like? What we find is that the previous iteration of this tagger was able to give us this kind of performance. So you can see the separation very clearly between background and signal. So the QCD is in blue, the Higgs signal is in orange. If we use this new tagger, actually, this based on this AI algorithm, we see much improved separation. Actually, it really is a very large improvement. And we usually quantify this in terms of the signal efficiency or the background rejection for a given working point. And so I won't go into the details too much, but basically we see a factor of 1.5 better signal efficiency. So we accept 50% more signal, and we can also reject 2.5 times more background using this kind of algorithm. So we see a big performance gain. And so now applying this to this picture that we started with, we can see that at least based on what this algorithm thinks it's a 97%, let's say, probability to be a Higgs to BB jet. And you can see the mass also turns out, which is not used in the tagger itself, the mass also turns out to be consistent at 130 GeV with the Higgs boson. So this is a very good Higgs candidate, actually. Okay, maybe I'll stop here and see if there's any more questions. Yeah, please. No, go ahead.
I'm trying to understand what is the use of AI because I have zero experience with it. So suppose that you have enormously powerful computer. Your calorimeters and other parts of your detector give you always the energy and the charge of the outcome, right? So now if you have enormously powerful computer, since you have energy and charge for every outcome, then in principle for every collision, you can reconstruct what is the particle that led to those jets, correct? Because it is simply kinematics, right?
Not quite. It's more like pattern recognition, right? So the way I think of it is there's always going to be ambiguity. So if you look at these kind of pictures, I didn't pick the most the hardest to classify. There's other pictures I could pick that are harder to classify in the sense that there's a real ambiguity between what is signal and what is background that no computer, or like just knowing the energies and charges, let's say, of the particles. First of all, our measurements are a little bit imperfect, right? So you don't know exactly the energy, the charge, yes, the charge, positive, negative, or neutral, but it's not like a perfect,
Okay.
let's say, determination. And also the jets themselves are stochastic. So you won't necessarily have all, you won't always have, like, let's say 100 particles coming out of this top jet. You might have, 50 or 100 or 175. And you might also lose some of the low energy stuff. You might lose some of the low energy particles. So it's not, let's put it this way. It's, if our detectors were perfect and ideal, then maybe you're right. Maybe we wouldn't have any need for AI because we could just like, yeah.
Okay, so it is not just a matter of having sufficient computer power. You have to deal with those elements you just described. Okay. Okay, I get it. Yeah. Are you going to explain later how do you look for unexpected? Because so far you're just sort of disentangling QCD events from Higgs decay, right? Will you talk about unexpected signals, hypothetical theories?
Unexpected signals?
Yeah.
Unfortunately, not in this talk. We do quite a bit of work on like anomaly detection algorithms and using AI for that as well. But yeah, I don't have it in this talk, unfortunately.
So that goes back to a previous question, because the way you describe what is not saved is lost forever, right?
Yes.
So what if 10 years from now, there is some bright theoretical model with some good justification, which to test it, it is in the data that you rejected in previous 10 years of the run?
Yes, I think about that, I think about that late at night, right? Like it stops me from sleeping, let's say. So yeah, then I agree. I think anomaly detection strategies where we just look for signals that don't conform to any other standard model processes is a really interesting way to go. And we're developing tools to try to do that kind of like anomaly stream, where we just stream out anomalous data, save it to disk, and analyze it later just to see what it could be.
Thank you.
Yeah. Great. And okay, so I think running a bit long or out of time, so I'll try to speed up a bit. But yeah, so one of the nice things about doing this kind of measurement or trying to identify Higgs bosons is that actually the standard model gives us a good way to tell if our Higgs boson identification is working, because there's a very similar resonance that decays to two bottom quarks, which is the Z boson, that is a similar mass. It's actually a little bit lower mass, so 90 GeV instead of 125. But it's also produced much more copiously. It's produced we have about 30 times more events like this than the Higgs to BB. So what we can do is actually use that, because we don't put the mass information at the tagger, we can actually use the Z boson to see how well our tagger is working and calibrate it using that. And one other word about how we actually do the statistical analysis is we also have to estimate our backgrounds. So we are from the rest of QCD, for instance. So for many things, we can estimate it with simulation. With QCD, this is a little bit more tenuous because our simulation is not always very good for QCD. And so what we do is we derive this QCD background using the jets that fail this double B tagger. So we actually look at the events that don't pass the double B tagger, and we use those events to basically predict the shape of this background in the region that passes the double B tagger, using like what we call a transfer factor. So I'll show you a little bit how that looks in real data. So this shows the distribution of events, of data events. It's hard to see the uncertainties there, so you can look at the ratio plot as well. But what you see is basically the main QCD background is shown in the dotted gray line, and you can see it makes up most of the events in this region that fails the tagger. You do see a small bit of events from W plus jets. So those are events from W boson decay to quarks, and as well as a little bit from Z bosons and top quarks as well, the production of two top quarks. There's also a little bit of signal in this region. But what we do is we take this events that fail this background prediction and then multiply them by a transfer factor that has some functional dependence. And then we predict the background. So now the multijet background you can see here in the dotted gray line has a slightly different shape. So we actually correct the background for that shape difference. Part of this is we call mass sculpting. So it's because the tagger is not perfectly decorrelated, uncorrelated with the mass of the jets. But here we see very clearly a big bump from the Z boson, which we expect. And this can tell us basically how well our tagger is working because we can basically measure the efficiency of the tagger for Z bosons. And then we can also measure the Higgs boson signal. So you can see here the Higgs boson signal seems to be pretty prevalent in this plot. This is integrated over many categories as well. So in the end, what we see is that the Z boson signal is basically what we expect, about 1 times the standard model rate. The Higgs signal is a little bit bigger than we expect, but it's not yet statistically significant. We see about 4 times the signal that we expected, but the uncertainties are still large. So it's still plus or minus 1.6. And so the excess ends up being about 2 sigma, 2 standard deviations, we call it. Which means that it's really only a hint of a potential excess, but it's not quite statistically significant yet. And so, but one other thing we can do is actually look at if there's any trends in the data. So we can actually look at trends, for example, in the momentum. So do we see something where like the deviation grows, for example, bigger as you go to higher momentum? And what we see is actually, in fact, that does seem to be the case, that there seems to be a bit of a deviation as you go to higher energies. And so one question we could ask is, well, what could cause this? And it turns out that if you have small shifts in these couplings where you have an extra sort of direct coupling between Higgs and gluons, you could very much create this kind of effect where you have a very large deviation in the momentum spectrum. So this is exactly the kind of thing that we might be sensitive to by measuring the Higgs boson, especially at these very, very high energies. So that's what we want to do. And to disentangle this effect and find out whether it's a real effect or whether it's just a statistical fluctuation, we need, of course, more data. And so to get more data, we actually need to increase the intensity of our beams. And so what that means is going from the picture on the left, where this is already pretty messy. There's lots of collisions happening simultaneously, lots of particles coming out, to the collision you see on the right, which is like just a huge jumble of stuff all happening simultaneously. So we need actually a lot more data in order and we need this intensity in order to collect more data, but this complexity comes with a lot of costs, and not just our computing complexity, but also it becomes harder to identify which collisions we actually want to save. So we are now working on developing smarter algorithms using AI to do this data filtering and find, the interesting events that we want to save, like events containing Higgs bosons. And so that's what I'll talk about in the next part. But I'll pause here to take more questions.
Hey, Gary, go ahead.
Yeah, I'm wondering where the technology is. When you said there were Higgs bosons every 4 minutes or something, are you detecting them every 4 minutes? Are they that frequent at the moment, or?
Yeah, they are, but we're not detecting them every 4 minutes in the sense that so there is some loss of efficiency from the trigger, which is what I'll talk about now. So we're not able to collect every single Higgs boson, but we instead do some filtering based on like features of the events that we think are interesting. So in particular, we look at, very high energy events or events that contain, certain combinations of particles. And that filtering is what we currently do, but we're now looking to see if we can do more advanced filtering, like, for example, using this kind of AI Higgs boson tagger directly in the trigger. Okay. Seeing no other questions, then I'll go through again. Sorry for taking so much time. Let me go a little bit faster. So to just set it up, there's different kinds of computing hardware that we could use for different tasks. And you can think of them as being on a spectrum between flexibility and efficiency. So more flexible means it's like less efficient, costs more power typically. And you also need, it's also slower. It takes more time to get data in, takes more time to get data out. Starting from the left, you can go to higher efficiency at the cost of flexibility, for example, by going to GPUs, which are these massively parallel architectures and allow you to do things like machine learning training and use, basically create this massively parallel computations. Going a little bit farther, we can actually use these things called field programmable gate arrays, or FPGAs, and I'll talk about that a lot more. But these are basically reprogrammable hardware chips where you're actually designing the hardware, programming the hardware to do a specific task. And then finally, there's ASICs, application-specific integrated circuits. And what these are very dedicated chips, which you can't change after you fabricate them. So you make the chip to do one specific job, and then you can never change it again. So that can give you the best efficiency and the fastest processing, but the least flexibility. You can never really change it after that's done. So the sweet spot, let's say, for this kind of edge computation might be in thinking about FPGAs. So how do we use these different kinds of computing models in the LHC? So again, we start with this 40 megahertz collision rate. The first thing we do is we process this, and each collision will have something like 1,000 particles. Our detectors have about 10 million sensors. And then we have these huge data rates that are coming off of the detector. So it could be as high as order of 100 terabytes per second, depending on how you count it. So then the first thing that we do is we actually to decide whether or not the event is interesting enough to save. And we do this using a two-step trigger system. The first step is called the level 1 trigger. And what this does is this is implemented in FPGAs and basically reduces the data rate down from 40 megahertz to 750 kilohertz. The next step is called the high-level trigger. This one's implemented in CPUs, and again, reduces the data rate down to about a factor of 100, down to about 7.5 kilohertz. And then finally, that's basically the set that we analyze. So we analyze about 8 kilohertz or 8,000 events per second. And you can see, again, we use application-specific integrated circuits when we're on the detector and need the fastest efficiency and the highest also radiation tolerance. FPGAs in the level 1 trigger, and then CPUs after that. And so again, I'll focus mostly on this FPGA level 1 trigger. So the goal of the trigger is to basically look at each event coarsely, reconstruct it, and then figure out which ones to reject. And we have to reject about 98% of them. And we have only about 12.5 microseconds to do it because we have a limited buffer where the event, if we take longer than 12.5 microseconds, we run out of space on the buffer and the event has to be thrown out anyway. So if you look at it, you can see that there's these different blocks that each one of which is doing a different job. So individual algorithms, like let's say within these blocks, usually have to be less than about a microsecond. And so these like tight latency requirements means that we need an FPGA design, and we can't use CPUs or GPUs in this process. And so instead what we do is we have these many algorithms running on actually 729 FPGAs. So this is showing each one of these little blocks is showing these little squares is a different kind of FPGA that's running on for one of these processing. And usually for individual algorithms, again, we want them to sort of fit on one FPGA because we want to be able to run them on many different events. And so one of these boards looks something like this. So this is an electronics board with the inputs are these optical fibers which bring in the data and then do the processing on the FPGA and then bring out the data as well through these optical fibers. And so again, the requirements at the system level mean that we are looking for algorithms that can be less than a microsecond and fit usually on one FPGA. So how do we program these things, these FPGAs? So say you wanted to program something like an addition function, which is called an adder. You usually have to write something like this kind of funny looking code, which is register transfer level or RTL code. This is then undergoes a process called synthesis, where you synthesize that into logic gates. So for instance, this adder can be implemented as these kinds of logic gates, which if you remember, these logic gates you can think of as these like core operations that can be done. So for instance, you might remember and is, if you do have 2 bits coming in, the output of the and is 1 if both of the bits coming in are 1, and otherwise it's 0. So these logic gates are really basically just lookup tables or LUTs, where you look at them and you look at the 2 inputs and you have a pre-specified output that you can just look up and give it that output. So how can we reprogram hardware? Well, if we lay out the hardware in such a way that basically there's a bunch of these programmable lookup tables, so these LUTs are distributed throughout some chip, and then we set up the interconnects between them that we can also change and reconnect and change them how we want, then essentially what we can do is implement any algorithm, because any algorithm can basically be decomposed into these lookup tables, and then we can connect the ones that we want to connect and get the input and output that we want. So this is essentially the logic behind FPGAs. So modern FPGAs are a little more complicated than that, but they are the same principle. Now there's the embedded components can also do more complicated things. So for instance, there's ones that can do multiplications. These are called DSPs. Some of them can do logical functions like these lookup tables, and then some can also be like memory units, so like store memory. And in general, we have these like high throughput cables, which can bring in a lot of data and bring out a lot of data. And you can run a bunch of computations in parallel, and they're relatively low power compared to CPUs and GPUs. So these are all pros, but of course, one of the main cons is that it requires a lot of domain knowledge to program, because we have to write this special language. So it makes it harder for physicists usually to get into it. So one of the aspects of our research program has actually been trying to make this easier for both scientists and machine learning experts to translate their algorithms, especially focusing on machine learning algorithms, into RTL firmware for FPGAs. So the typical cycle looks something like this. You maybe train some model using your machine learning framework. You might actually compress this model. I'll talk a little bit about that. And then you can use this tool, HLS4ML, to basically convert this into a project. We use what's called high-level synthesis, which is a modified version of C++, to actually code it up instead of coding it up directly into RTL. And then vendor tools from either Xilinx, Intel, or Mentor can be used to turn that HLS code into RTL for FPGAs or even for ASICs design if you want. So what can this be used for? So we actually benchmark this with a simple neural network tagger. So this is a simple jet tagger, which actually tries to classify these 5 categories of jets and is able to do it accurately about 70 to 80% of the time. And so here you can see just like kind of one example of this algorithm that can run on an FPGA. In general, we can map these algorithms, these operations of a neural network to an FPGA, because as you can see, it decomposes into really simple atomic pieces. There's the multiplications, there's the additions, and then there's the activation functions. And all these things kind of map nicely onto the DSPs and the lookup tables that we have available on the FPGA. And so in the end, if we look at this neural network, it basically looks like this. So you can see it's basically the same one as I was showing you earlier, only it's a little bit larger. And so the question is, how many resources will this take? Does it fit on the FPGA? And if it doesn't fit, can we reduce the model and make it fit? So the general principles behind doing this are called co-design. So this is sort of the development loop between the algorithm and then the hardware. And so what we can do to this algorithm is actually do a bunch of things to reduce it. We can compress the algorithm, which is when we remove operations that we don't actually need. So we might actually make it smaller, like use less neurons, or we might just like prune away these connections that you see here. The next thing we can do is quantization, which is when we reduce the precision of the operations. So usually we do 32-bit multiplications and additions on like CPUs. But here we can, on the FPGA, we can reduce this to 16 bits or 8 bits or even lower. And this is kind of like, the analogy here is representing it by like this low resolution image. And then finally, we also want to think about parallelization. So how fast do we need the neural network to be versus how costly the resources will be. So in the end, we can show you basically some performance of what this neural network looks like on the FPGA. We find that instead of 32 bits, needing 32 bits, which is the typical thing you use on a CPU, we can actually achieve the full performance, so like 100% of the full performance with only 6 bits when we train it in this way. And this means that we can use basically a much smaller fraction of the resources. We can see we're actually below 10% of the resources on this particular FPGA. So it very much fits within the FPGA comfortably. The next thing we can look at is how fast we can run it. So does it fit within the latency requirements? And we have a handle that we can tune here, which is we call the reuse factor, which is basically how many times you're reusing the resources of the FPGA. So a reuse factor of 4, for example, would be reusing the same resource 4 times, whereas a reuse factor of 1 would be instead spreading that out, parallelizing it as much as possible, and only reusing the resource and only using the resource once. And so what we can see is there's this natural trade-off between the resources and the latency. So if you are okay with using more resources, you can get to a lower latency. And in fact, what we see is that for this algorithm, you can get down to 15 clock cycles, which corresponds to 75 nanoseconds. So actually less than 100 nanoseconds to do one inference of this model. And so again, the algorithm comfortably fits in the latency requirements, which were like less than a microsecond. So about 10 times less than we needed them to be. Okay, so looking beyond LHC, so of course the LHC is a big use case for this. We need fast algorithms for our on-detector readout as well as for our trigger at 40 megahertz. We also turns out we can use this to control aspects of the accelerator chain. There's also use cases in neutrino physics, which is a related branch of high energy physics, which studies neutrinos. There's also some use cases in multi-messenger astronomy where we need to quickly sort of take data or alert other experiments when certain things are observed in one astronomy experiment versus another. There's also ways that we can sort of control microscopes in electron and X-ray microscopy and do better experiments using this kind of real-time AI. And finally, just a little note that we're also looking at pushing devices to the lowest possible power, not just the lowest possible latency. And so, for instance, we're exploring applications in, for example, this device that you can buy from Xilinx, which is like $100, and see if we can provide benchmarks for scientific use cases for very low power applications. Okay, so to summarize, in general, for the physics side, so precise measurements of the Higgs boson may hold the key to discovering new physics at the LHC. There's intriguing mysteries related to dark matter, the matter-antimatter asymmetry, potentially new heavy particles, also the Higgs self-interaction and the stability of the universe actually all wound up in better understanding the Higgs boson, which is what we want to try to do. To answer these questions, though, we actually need to increase our data. And so to cope with this increased data rates, we can actually use AI in real time to improve both the performance of our detectors and our accelerators and save potentially overlooked data. So data that we might be currently throwing out or we will have to throw out in the future because of the increased data rate. HLS for ML is this tool that we've developed for translating machine learning algorithms into hardware for science. And ideally, this will hopefully give us the ability to do more sophisticated triggers, use smart sensors, and also have our detectors essentially run autonomously. So the final slide to answer the question at the beginning. So what do Mars exploration and particle physics have in common? So in both cases, there's not enough time to send data back to some CPU. In the Mars case, there's not enough time to send data back to Earth. So processing and these decisions have to happen at the edge in real time, so where the sensors are on Mars. Similarly, in particle physics, we don't have the time. We need to actually make our decisions on the detector or just after the detector and use sophisticated algorithms. And then finally, in both cases, of course, we're really trying to explore the edge of the unknown. So thank you.
Thank you. Give a round of applause. Confetti. I want the Zoom like fireworks or something.
Yeah, exactly.
All right. Yeah, if you've got a question, please raise your hand and I'll try and queue them up in order. All right, I'm going to ask a student to go first since the faculty members have been monopolizing. So Gustavo, fire away.
Yeah, thank you for the presentation. Is there a book that you recommend on machine learning?
Ooh, yeah, there's tons of interesting books out there. I'm trying to remember. There's one called Data Reduction. I'll have to look it up because I can't remember what it is. But we used it in this Caltech machine learning class, and it was very, very good, like introductory explanation to machine learning. There's also on the archive, if you don't want to pay for a textbook, there's also on the archive, if you Google, there's machine learning like kind of textbooks specifically for physics. So that I thought that's interesting. And one of them is I think called like a low bias, high variance guide to machine learning for physics or something like this.
Yes, yeah, one of my friends, I believe, is a co-author on this. Yeah.
Okay, yeah, great, great. Yeah, so that's just one example, and you can find that. I think that one is another good one, and it's free. So.
Okay, thank you, thank you. I was wondering if there's an equivalent of like the Griffiths book for quantum mechanics, in which the language is really friendly. If there's an equivalent for machine learning, so thank you for your suggestion.
Yeah, no problem.
Yeah. Here, I think Christian, you had your hand up there.
Yeah, thank you so much. Yeah, thank you for your presentations. Pretty interesting. This is a quick question. Is it possible that you can use AI to manipulate the velocity of some of these collisions or particles? Will that be a possibility in the future? I don't know.
So does that mean going to higher energy collisions, or just yeah?
Yeah, I mean, I'm saying like physically manipulate, engineer, like get inside the particles. That can be possible.
Yeah. So, most, at least not in the short term. So right now, you have to remember how small these, basically as far as we can tell, these particles, are elementary. So we can't like break them up anymore.
Oh yeah.
And the resolution. So we would need really high resolution detectors. So so maybe AI could help us develop better detectors that have finer spatial granularity. So you're right. So there is like kind of a thread of like thinking of using AI to improve our detector development. So there is that. But yeah, I think in order to like really think about how we, so there's two things. To make the collisions higher energy, we need basically better magnets. And so we need better magnet technology. But that is something that potentially AI could help us understand how to develop better magnet technology. And the other thing is the detector technology in order to actually like look at these in more detail.
Yeah, it'll probably be moderately expensive. So yeah. Yeah. Thank you so much. Thank you.
Yeah.
Lorenzo.
Hello again. Thanks for the talk. That was really interesting. My question goes back to the proton on proton collisions you were talking about earlier.
Yeah.
It's still a little vague to me as to what you mean by special or like more interesting collisions. What are the sort of characteristics you're looking for there?
Yeah, that's a good question. So maybe I could just, so this is an example of an interesting collision. Both of these jets are very high energy. So this is a PT. So this is the momentum of this jet basically is almost 1 tera electron volt. So this means, so the proton mass is a good scale to keep in mind. The proton mass is about 1 GeV. So this is about 900 times as energetic as the proton mass. And so the same thing is actually true of this one. This one's also that high energy. So by an interesting collision, I mean, for example, this one, which is basically just has 2 very high energy particles going in opposite directions, which is like a typical, like, let's say, configuration for the particles to come out. Other interesting collisions might be if they have a certain multiplicity of a particle. So for instance, muons are very interesting particles that aren't produced super often. And so you might see, for example, an event with 4 muons. If an event has 4 muons and then they're high energy enough that we can detect them easily, that is a very interesting event. That doesn't happen very often.
Okay, I see. Thank you.
Yeah.
All right, I think, first of all, I just want to say, if anyone has to go, I know that classes are starting. That's absolutely fine. And so maybe we'll just take these last 2 questions, Milan and then Gary, to wrap it up.
Actually, I have a couple, sorry. Can you hear me? Yeah. I have a couple of questions, but let
Turn
me
it
be
to
quick.
1, Milan.
I have only one?
Go on.
Okay. Okay. Well, obviously you're building a Skynet here. I think that's, and I suppose all of this stuff is already on cruise missiles and in a missile defense, right?
Well, maybe. I don't personally work on anything related to defense. I'm sure technology similar to this could be used for that, but I would not advocate for that. I'm definitely in favor of using these tools only for science.
Right. So quickly, because Paul is going to cut me off, at which point in your career or in your education did you select AI as your tool and machine learning?
I guess as a postdoc is when I started looking at it. Seriously, I had taken some courses in graduate school and learned a little bit about it. But I think I was a little bit on the skeptical side for quite a bit of time, until I saw that there really was things you could do with the AI, like just pattern recognition things you could do that we really couldn't do any other way. And also it's really just a natural continuation. In hydrogen physics, we've been using machine learning since the 1980s. In fact, I found a article published that says a gluon that's called like gluon jet tagger in the trigger, and it's from 1980. So it's like we've in many ways, and it's a neural network. Sorry, it's like neural network gluon jet tagger in the trigger or something. And it's like I could have written a paper that's titled that like today. It would maybe have be slightly bigger, you know, algorithms or whatever, but it's basically the same idea. Yeah.
Thank you.
Gary, go ahead.
Wow, I got the last question of the last seminar. This is an unusual honor, especially since I'm not in the physics department. I guess I have lots of questions, but this is the one that's troubling me at the moment. You have all this fancy stuff to separate the Higgs boson events from other events. And I'm wondering whether you're deliberately excluding possibly even more exotic things that may be happening and not being captured. Are you? Surely that's something you have to worry about.
Yeah, I think so. I think, and so I'll clarify that this is like one specific analysis, one specific search that's done and measurement for Higgs. But of course, the CMS collaboration, we're interested in, we do, you know, hundreds of searches, hundreds of different teams are working on different aspects of looking at the data in different ways. And yeah, so you're totally right. I might be throwing away events that might contain the new physics, but I hope the hope is that by designing our overall physics program in such a way that, you know, there is a group that's working, and I also work on this. There are groups working on, you know, general search just for exotic new physics. So for instance, long-lived particles that may be rejected by you know, MyCuts or something, but they would still be the signal for this other analysis. So that is the hope, that we're all doing.
But you're deliberately eliminating the other signals, right? The really interesting events, maybe if they're there, you're not passing, you're not collecting, you're not storing, right?
Yeah. So you're saying, are we throwing them away at the trigger?
So other groups working with the same data, well, they're getting the data that looks for Higgs bosons, right? So they're
right. Yeah, but there is not necessarily just one trigger. We call it a trigger path. There's not just one algorithm running on the trigger at any given time. It's really
Ah.
an OR of many paths. And one of them actually we're developing now is a dedicated anomaly trigger, which is looking for something that doesn't look like anything else. Yeah.
Okay, got it. Thank you.
Awesome. All right. Well, I'm sure Dr. Duarte also probably would be happy to answer any questions via email.
Yeah. Definitely.
And I really appreciate also giving some advice to folks who are interested in learning more about machine learning, deep learning in particular, some resources there. I appreciate that a lot. I just want to say thank you again for joining us and give another round of applause, sticking around overtime. And we hope to have the chance to host you in person in the not too distant future.
Yeah, not too far away. So definitely.
All right, cool. Well, thank you, everyone. This was the last colloquium of the academic year. So I guess I can, in one sense, say, see you next year.
Thank you so much for seeing you.
Thanks, everyone.
Thank you.
Bye-bye.
All right.